Hey everybody. So this is the last of our meetings this semester, as it were. And here we present the last exercise for you to show mastery of the material that we've covered this semester. In the last, albeit long, video, we presented the concepts of automated logical reasoning insofar as we defined an executable specification, a program that runs, albeit in the formal language of Lean, that essentially implemented the syntax and semantics of propositional logic. In this lecture and test section, we're going to write a bunch of interesting and important propositions in propositional logic. And then we're actually going to implement a validity checker. And we're going to check to see whether each of these expressions is valid. So the first thing we'll do is we'll look at the expressions and reason about them informally in our mind and come up with expectations for whether they're valid or not. Then we'll implement that validity checker and we'll find out for sure, if our validity checker is correct, we'll find out for sure whether or not our intuition about the logical validity of these propositions is correct. So let's head on over to VS Code, where I've already set up a file that we can work with. Okay, I'm going to ask you to go ahead and create in your own directories, in your own My Work directories, a file called proposition px_validity.lean. You can see that I've created that here. So you can create this file from scratch, and I'll ask you to go ahead and just, it's not particularly long. I'm not going to ask you to type the comments in, but it's worth going through the effort of typing this in this material to make sure that you're processing it fully rather than just looking at sort of impenetrable code. So here's the idea. We're going to start by importing our definition. Whoops, here's px validity. We're going to start by importing px.lean, this file, which is the one that we presented yesterday. So this is the syntax and the semantics of propositional logic. So let's look at the px_validity file again. So we're going to import those definitions here. So we now have within this file access to our definitions, our specification of the syntax and semantics of propositional logic. We're going to open two namespaces from that other file, the definition of the propositional of the syntax and of the type that defines our indexed collection of propositional logic variables. Okay, so go ahead and in your own file, open up these two namespaces. Okay, now all we're going to need in order to present the core material of this, this exercise to test your ability to use what we've learned this semester, all we need are three variable expressions in propositional logic. Okay, so I'm going to call them P, Q, and R. Each one is an expression in propositional logic. In particular, each one is a variable expression. And let's see, maybe I should split my screen to the right. And on the right here, we'll look at this file. We'll look at the syntax and semantics. And let me close out that project browser on the left. So here's px validity. Here is the syntactic definition of propositional logic. Okay. So we're defining P to be a value of type px, in other words, a proposition in propositional logic, a logical expression in propositional logic. And in particular, it's a variable expression built by the var constructor, taking a variable object of this type as an argument. Variable objects are built by applying the v constructor to a natural number. So here we have our first variable in our infinite set of variables, second variable in our infinite set of variables, third variable in our infinite set of variables. And those are the only ones we need to use in this example. We apply the var constructor, the var expression constructor, to each of those three variables to get a variable expression in the syntax of our language. So P, Q, and R. Now just think of them as variables that we can use in propositional logic expressions. And by using variables here, these variables could really stand for any propositions at all. So for example, Kevin is from Charlottesville, Mary is from Richmond, and Tom likes to play the piano. Okay? Or P could mean, water is wet, Q could mean it's raining outside, and R could mean, the streets are running with water. P, Q, and R could represent any propositions at all. And what we're going to do then is we're going to put P, Q, and R together into larger propositions, understanding that they could refer to any propositions at all. And we're going to ask whether the larger propositions that we're going to build are always valid. Okay? So these are three variables. You don't need to type in these comments. Okay? So these are three variables. These three variables are sufficient to define a whole family of important propositions. And these propositions that we're going to look at are really important in both propositional and predicate logic. Okay, and so here they come. What we're going to do now is read them, translate them into English, think about why they are not valid. Okay, and I have a bunch of valid ones with a few invalid ones sprinkled in. We call an invalid rule of reasoning a logical fallacy. Okay, and so sprinkled in amongst these various important standard rules for reasoning, we have some fallacious rules as well. And when we check these rules for validity using the validity checker that we're about to build, it should tell us which of these rules really is valid, which is to say true under any interpretation. Whether the constituent propositions are true or false, the question is whether these larger propositions remain true, again, under any interpretation. So we talked about that a bit yesterday. Okay, so let's turn to this list of propositions. And let's talk about them. On each line, I define a proposition, I give it a name, okay? And then to the right of the colon equals is the proposition itself, okay? So you recall from Colab that we've substituted this symbol for the ordinary arrow in Lean. There are problems overloading that operator. So we're going to read this as P implies Q implies P and Q. That's one way to read this. That's just translating this first proposition into English in a very sort of, straightforward way. A better way to read this is if P is true, then if Q is true, then P and Q is true. Okay? So something important to note here is that this symbol is right associative. So I said, if P is true, then the rest is true. Okay, the rest says, well, if in the context in which P is true, Q is true, then P and Q is true. In other words, if P is true and then if Q is also true, then P and Q is true. Okay, under our semantics for propositional logic, what's the rule for evaluating P and Q? Well, you evaluate P, you evaluate Q, you map the and symbol to Boolean and then you compute the Boolean and of the Boolean values of P and Q. So if P evaluates to true and Q evaluates to true, then P and Q should evaluate to true. And that's what we mean by and in logic. It means that both of its arguments are true. So this larger proposition then says, if P is true, then if Q is true. And so now we're in a context in which we've essentially assumed that both P and Q are true, then P and Q is true. So first question to ask yourself is, do you believe that? If P is true and if Q is true, then is P and Q true? If it's true that Kevin is from Charlottesville and it's true that Mary is from Richmond, is it true that Kevin is from Charlottesville and Mary is from Richmond? And intuitively, the answer is absolutely, right? This is a valid rule. No matter what propositions P and Q stand for, this rule seems like a valid rule of reasoning. And indeed it is. So now the next question is, what does it really mean for this to be valid? Well, what it means for this to be valid is that whether P is true or false, whether Q is true or false, in other words, under all possible interpretations, under all possible truth values for P and Q, the question is this overall proposition true? So we've reasoned about one case so far. If P is true and if Q is true, then this certainly is going to evaluate to true. But what if P is false? Now the question is this whole proposition still true? Because to be valid, it has to be true under any interpretation of the variables. So suppose that instead of being true, P is false. So now we have false implies a whole bunch of other stuff. And the question is that true? To understand the answer to this question, you have to go back to the truth table for the implies operation. Implies is a Boolean operator in logic. And when is it true? It's true if both the antecedent and the conclusion are true, or if the antecedent is false, right? The only time that, right. So in other words, if P is false, then this whole proposition is true no matter what. Now, if P is true and Q is false, well, we have if P, then the rest is true. Well, if Q is false, then the rest doesn't matter, because if the first argument to an implies is false, then the entire proposition evaluates to true. Okay, and so if you write out the truth table here, let's do that just as an exercise for this one case. Okay, we have two propositional variables here, P and Q. So let's write P, Q, and P and Q here. Okay, and this will be the headings for our truth table. So let's look at all, in this case, there's 4 possible interpretations. We're just ignoring the value of R in this case. It's irrelevant, so we'll focus our truth table on P and Q. If we have P is false and Q is false, then the question is this proposition true? And the answer is yes, because if P is false, let's replace this with P implies Q, implies P and Q. That's what we're interested in. So we have 3 columns in this table, okay? And we're going to look at whether this big old proposition, P implies Q implies P and Q, is true under all possible interpretations of the variables in that expression. There's only 2 variables. Each variable appears multiple times, but there's only 2 variables whose values we need to worry about. So let me add a couple of spaces there and a couple of spaces here. Good. Okay. So the question is, if P is false and Q is false, is this expression true? And the answer is yes, because if P is false, then this is P, false, and this is an implication. P implies all the rest. Implication is right associative, so things group like this. Okay. And the definition, the truth table of implies in Boolean algebra, in the semantic domain of propositional logic, is that if the first argument to an implies is false, whether or not the second argument is true, the overall formula evaluates to true. Okay, so here we have that this is true. Now, if P is false and Q is true, what do we have? Well, If P is false, well, then the rest doesn't really matter again. So this evaluates to true. Okay. Now, if P is true and Q is false, what do we have? Well, P implies, so P is true, implies, and then what's this? False implies P and Q. Q is false. Well, false implies anything. False implies false, and false implies true. So this is true implies true, because Q is false, and so this is once again true. And finally, in the case where P is true and Q is true, this overall implication is true, and so we have a valid rule of reasoning here. Okay, this is a valid rule of reasoning. And to translate it into English again, it says, if one proposition is true, then if another proposition is true, then their conjunction is true. The and of those two propositions is true. That makes sense? Good. Okay, so this is the first proposition that we believe is valid. So we expect that when we test these propositions for validity, mechanically, we expect that this is valid. And I'll write it like that, okay? And the reason we expect that it's valid is because under all possible interpretations of the variables that appear in this formula evaluates to true. Okay, so stop the tape here, the video, and go over this with some care and convince yourself that, that what I've said here makes sense. Okay, the key to understanding this is to remember the truth table for implies. Okay, what does the truth table for implies look like? Let's actually sort of, do a little cheating here and make sure that you remember what the truth table looks like. I'm not going to give you every last element of it, but here's what you would do. If P, Q, and P implies Q, what's the truth table for implies? And we have the case where both arguments are false. We have a case where, good. So if both arguments are false, go back and look at what we did in the section on Boolean algebra. What's the truth table for implies? And you're going to get a true there, right? Okay. If P is false and Q is true, what do you get here? If P is true and Q is false, what do you get here? And if P is true and Q is true, what do you get here? Okay. You have to go back and reconstruct in your mind the truth table for implies. This is it. And if you fill in the answers here correctly, okay, and you can see, false implies anything, so it's pretty clear that this has got to be what? False implies false, false implies true. Both of those are true. So that's going to be true. Okay, we know that true implies true is true. So that helps here. And the only case where an implication is false is where the premise is true and the conclusion is false. Okay, so I cheated and I gave you the answer. Okay, and this answer here can actually help you with one of the problems in the previous section posted yesterday. Okay, so given that this is the truth table for implies, okay, then you ought to be able to see that this is the truth table, if you will, for and intro, this proposition that I've called and introduction, this proposition must be valid. Valid in the sense that if you build a truth table, it's true for every possible combination of truth values of P and Q. Okay? Good. Okay, I'm not going to spend as much time on each of the following rules at this point, but I want you to go and think about them on your own. So, and I'm not going to spend too much time trying to explain the names that I've given to these rules. The import of these names is that these become the syntactic reasoning rules of predicate logic. Okay, these become the rules for building proofs in predicate logic. Okay, good. So here's the second rule. And again, we're not in predicate logic here, we're just in propositional logic. So P and Q are propositions that are either true or false. And what this says is, well, you take a second and try to translate this into English. Okay, there's something to notice here, which is that the binding power of and, I should tell you, is higher than the binding power of implies. So adding those parentheses just makes explicit what that already said. So what does this say? This says P and Q implies P. That's a straightforward translation of just the symbols. A better way to read it, though, is if P and Q is true, then P is true. Okay? Is that valid? If it's true that Kevin is from Charlottesville and Mary is from Richmond, then is it true that Kevin is from Charlottesville? And the answer, of course, is yes. Okay, so intuitively, this is a rule that invariably, intuitively at least, makes total sense. If something is true and something else is true, then the first thing is true. Okay, and we have a similar rule that says if two things are true, then the second thing is true. So again, we can disambiguate here by putting in parentheses, and it's important to know that the and symbol has higher binding power. This is just order of operations than implies. So if P and Q is true, then Q is true. A really nice exercise. How about we do this as a little test exercise, okay? Test exercise. You build the truth table. For this. Okay. Here we built a truth table for something more complicated, letting P and Q vary over all possible combinations of values, and we found that this formula is valid because invariably it's true under each of these possible interpretations. So an interpretation is really just a row of a truth table. That's exactly right. Okay, so here you can build a truth table for P and Q implies Q. Okay, so what's that going to look like? Let's get it started. Okay, so here we have P, here we have Q, and here we have P and Q implies Q. Okay, so why don't we actually, yes, good. So, okay, so we have false, 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 and something here. Okay, we have false, false, true, true, and something here. We have true, true, and false, false, and something here. And we have true, true, and true, true, and we have something here. So go ahead and reason about, if P is false and if Q is false, then reason about this. If P is false and Q is false, then this has to be false, and false implies anything. So false implies false is true, false implies true is true. So in this case, we just have to have a true here. Okay, so go through the exercise in your mind of evaluating this expression for each possible interpretation of P and Q, and just fill in the resulting slots in this table, and you'll see that you get an answer that we expect. Okay, so let's look at the next two rules in combination. They're called or intro left, or introduction on the left, and or introduction on the right. And what the first one says is that if P is true, then P or Q is true. Okay, so and once again, or has higher binding power than implies, and so really you could put parentheses in there like that if you wanted without changing the meaning of this. A little easier to read if you're not used to reading this stuff. The first one says, if P is true, then P or Q is true. Now, given your understanding of Boolean or, this totally makes sense, right? If Kevin is from Charlottesville, then Kevin is from Charlottesville, or 2 equals 3. Because Kevin is from Charlottesville, or 2 equals 3 is true if either of the constituent propositions is true. This is, think about Boolean expressions in Java or Python programs, right? X or Y is true if X is true, or if Y is true, or if both of them are true. It's only false when both parts are false. Okay, so if P is true, this says then P or Q is true, and this one says, well, if Q is true, then P or Q is true. And so intuitively, we expect that each of these is valid. So let's put our expect here. We'll put expect is valid. Okay, we expect this one to be valid. We expect this one to be valid. And we forgot to put our little expectations in here. We expect both of these rules to be valid, right? Okay. Now, or elimination is the hardest of these rules to understand intuitively. So here's what it says. It says, if at least one of P and Q is true, in other words, if P or Q is true, which means that at least P is true or Q is true, at least one of them is true, then if it's the case that if P is true, then R is true, and then if it's also the case that if Q is true, then R is true, then R must be true. Okay, so let's do that again. If at least one of P or Q is true, and if whenever P is true, R is true, and if whenever Q is true, R is true, then R must be true. Okay, if there are two situations that imply that R is true, let's call them P and Q, and if at least one of those situations holds, then R must be true. So, you know, it's a good idea to you know, think about English language rather than kind of symbolic examples here. So let's give an example of where this rule of logical reasoning makes sense. How about we'll say it's true that it's raining, or a sprinkler is running. Okay, that's our P or Q. So let's assume that this is the case. If this is the case, then if it's also the case that, well, P means it's raining, so if it's raining implies that the ground is wet. Okay, so here we have it's raining, or the sprinkler is running. Here we have, if it's raining, then the ground is wet. That's what R is, the ground is wet. Then we have also that if a sprinkler is running, the ground is wet. Then what must be true? If it's raining or a sprinkler is running, and if it's raining, the ground is wet, and it's also the case that if a sprinkler is running, then the ground is wet, then what must be true? Well, it's either raining or a sprinkler is running, and here's the thing. Here's how to say it in English. So in either case, there's two cases here. It's raining or a sprinkler is running, and in either case, the ground is wet. Well, then the ground must be wet. Okay. Okay. And so this is a rule that says if we know that this is true, and if we know that this is true, and if we know that this is true, then this must be true. Okay. So this formula in propositional logic becomes a way of reasoning from known facts to conclusions that we can deduce based on those facts. Okay. So this is the rule of or elimination. Now this is a rule that has three different propositional variables in it. This is an expression with P, Q, and R. And that's as many propositional variables as we're going to need here in any of these examples. So to determine whether or not this expression is valid, we'll require a truth table with how many rows? We have 3 possible columns, P, Q, and R. Each of the P, Q, and R can be true or false. How many possible combinations are there? We covered this in the chapter on Boolean algebra. Well, with 3 Boolean variables, each taking on 2 possible values. There's 2 possible values for the first one, 2 possible values for the second one. That's 4 combinations. And for each value of the third one, you have those 4 possible combinations. So there's 8 possible combinations of Boolean values for 3 variables. So the truth table here would have 8 rows. Okay, and the idea is that if you evaluate the truth of this expression using our rules for evaluation, under any of those 8 interpretations of P, Q, and R, well then what do we expect? We expect that we're going to find that this formula is valid. Okay. That is pretty nice. Okay, good. Okay, now we have the next 2 rules are really very simple to understand, and they're sort of a special case of the AND introduction rules. The first one, we call it if intro, and I just give 2 different variants really of this rule. The first one says if whenever P is true, Q is true, then whenever Q is true, P is true. In other words, if P implies Q and Q implies P, then P is true if and only if Q is true. So what does P imply Q mean? It means if P is true, then Q is true. What does Q implies P mean? It means if Q is true, then P is true. So if P implies Q and Q implies P, then basically they imply each other. And that's what that 2-headed arrow means. So we can say if P implies Q, then if Q implies P, then P and Q imply each other. Or we could say P and Q are equivalent. What does it mean for P and Q to be equivalent? Well, go back and look at the truth table for equivalence. The truth table for equivalence says this is true if both P and Q are false, or if both P and Q are true, and this is false otherwise. And that's, in other words, you can almost think of by implication, if and only if, equivalence as being the same as equality for Boolean variables. Okay, so if P implies Q, then under that assumption, if Q also implies P, then it must be the case that P and Q are equivalent. So you can convince yourself that this is true by doing the truth tables, but let's spend 1 more minute thinking about what this really means. So let's suppose that P and Q are both false. Okay. Well, this is true because false implies anything is true. True implies, well, this is true because Q is false, so this is also true. So that this says if true, then if true, then, and if P and Q are both false, this evaluates to true. So we have true implies true, true implies true is true. So we have true implies true, which is true. So this whole thing evaluates to true. Now, if P and Q are both true, well, true implies true is true. True implies true is true. And you get the idea. Now, what happens if P is true and Q is false? Well, here we have let me ask you to work it out for yourself, okay? Write out the truth tables if you need to. So these 2 rules, this rule says, if P implies Q, then if Q implies P, then P is equivalent to Q, or P is equal to Q. Okay? This rule, the difference here in the way I've written this rule is I've used an and here instead of an implication. The way to read this again is if P implies Q, If you're just translating the symbols, you would say then, but I like to read this kind of chain of implications as an and. Okay? If P implies Q, then if that you assume that P implies Q, then if you also assume that Q implies P, then this is true. That's how you read this, okay? So a nice way to rewrite it in logical symbols that is more akin to the way you would say this in English would be, if P implies Q and Q implies P, then P is equivalent to Q. Okay. And if you wanted to be really cool, I suppose that you could prove using our the validity checker that we're going to develop in a few minutes, you could actually write a proposition that says this is true if and only if this is true. And we would expect that that's a proposition that would also be valid. Okay, awesome, good. Okay, the next two rules are simply, they're kind of like the and elimination rules. The and introduction rules say if P is true, then if Q is true, then P and Q is true. The elimination rules say if P and Q is true, then P is true. Down here, the if introduction rule says if this is true and this is true, then this combined thing is true. And here the elimination rules kind of undo the if and only if. It says if P is equivalent to Q, then P must imply Q. Okay. Similarly, if P is equivalent to Q, then Q must imply P. Because what does P if and only if Q really mean? It means that P implies Q and Q implies P. So if P implies Q and P implies, if P implies Q and Q implies P, then P implies Q. And similarly here. Okay. Now, the next one I want to highlight because this is a rule that goes all the way back to, the famous Greek polymath and logician, Mr. Aristotle. Okay. And looking at the rule here, basically says, well, if P is true and if P implies Q, then Q must be true. So let's take an English language example of that. Let's let P be, it's raining. And let's let P implies Q be, if it's raining, then the streets are wet. Okay? So if it's raining, then if whenever it's raining, the streets are wet, then what? Then the streets are wet. If, let's say, if it's raining, then if whenever it's raining, the streets are wet, then the streets must be wet. Okay? If I'm over 150 years old, and if being over 150 years old implies that I'm dead, then what? I must be dead. Okay, so make up a bunch of examples of your own here, and the order of these we could put this in the other order if you want, like this, like this, and it doesn't really matter. Okay, so if being over 150 years old implies that you're dead, then if you're over 150 years old, then you're dead. Okay, and you can see actually, if you put the parentheses here, then this is really actually a trivial kind of a proposition. Anything implies itself. True implies true, and false implies false. Good. So let me actually put it back the way that we had it to begin with. And that looked like this. Okay. So let's see if we can come up with one more example. I think the famous example from Aristotle went like this. If Socrates is a man, I'm sorry, I think Aristotle might have used the masculine gender here. I'll use person, okay? If Socrates is a person, and if being a person means that you're mortal, then Socrates is mortal. Okay. This is called arrow elimination contemporary logic, it was one of Aristotle's famous syllogisms, which were his rules of valid reasoning. Okay? This says if something implies something else, and the first thing is true, then the second thing must be true. Here's another really interesting way to think about this, linking to what we've been learning in Lean. It says if you have a value of type p, and if you have a function that takes any p and returns a q, then you can always get yourself a q. Okay? By applying this function that takes a p and returns a q to this p. So if I have a p, and if I have a function that when given a p returns a q, I can get myself a q. That's a little extra credity thing. You don't have to worry about that. If you found that confusing, skip by it. If you found it intriguing, then you're onto something really important. So, think about coming and taking the course next semester. Okay. So that's the rule called arrow elimination. This is another one of Aristotle's syllogisms, and today it is called syllogism. And it says if P implies Q and if Q implies R, then P implies R. So let's give an English example of this. If it's raining means that the streets are wet, and if the streets being wet means that the streets are slippery, then that means that if it's raining, then the streets are slippery. Okay, come up with an example of this on your own. Okay, if something, then something else, and if that's something else, then something further, then if the first thing is true, then the further thing must be true. Okay, if 10 is greater than, well, maybe that's not a very good example. Okay, that's not a very good example, so let me not do that example. Come up with some examples on your own. Do we expect these rules to be valid? Let's go back and look at these rules. If P implies Q and Q implies R, then P implies Q and Q implies R, and that's really the meaning of P if and only if Q. P if and only if Q simply means that P implies Q and Q implies P. In other words, this is true whenever both of these things are true. And in fact, later on, to prove this, what we'll have to do is prove both of these implications are true. Good. So we expect actually this to be valid. And this one, and these as well, right? If two things imply each other, then certainly the first implies the second, and then on the second line, the second implies the first. This one we expect to be valid if some condition holds, and if whenever that condition holds, some other condition holds, then that other condition must hold. Because whenever the first condition holds, the second condition holds, and the first condition holds. So if you assume the first condition holds, if the first condition holds, then whenever the first condition holds, the second condition holds, under both of these assumptions, it's inevitable that the second condition will hold. Okay, so intuitively, this is a valid rule of logical reasoning. Similarly, we expect syllogism to be valid if whenever P is true, Q is true, and if whenever Q is true, R is true, then it must be the case that whenever P is true, well, that makes Q true. And we've also assumed that whenever Q is true, R is true. So whenever P is true, R must be true. Okay, and once again, there's two different levels at which you can think about the validity of these propositions. First, intuitively, these rules make sense. Okay, I mean, these are just the way we think when we're thinking rationally. These are just ordinary, everyday rules of scientific, rational reason. Okay, and they make sense. Okay, if everyone from Charlottesville is nice, if being from Charlottesville implies that you're nice, and if being nice implies that everyone loves you, if being from Charlottesville implies that you're nice, and if being nice implies that everyone loves you, then being from Charlottesville implies that everyone loves you. Okay, so think about it. There's no counterexample to that sort of reasoning. It just makes sense intuitively. And to show formally that this is a valid proposition, basically you have to write out the truth table. There are 3 variables here, so there are 8 rows in the truth table. and you have to evaluate this expression under every possible interpretation of P, Q, and R. Okay, so let's do one. Let's take that proposition. Let's suppose P is true. So we'll put trues in for all of the P's. Okay, let's suppose Q is false. So we'll put Q's in for all of the falses. And let's suppose that R is true. I'm just making this up. You know, we expect this whole thing to be true. So true implies false. What does that evaluate to? Well, that evaluates to false. Right? Look at the truth table for implies. A implies B is false if and only if A is true and B is false. So we have a case here where A is true, B is false. So this implication is false, evaluates to false. Now let's look at this one. Okay. So this is false implies true. Is that true or is that false? Well, in the truth table for implication, false implies true is true. False implies false is true. So this is true. Okay. And what about this one? True implies true. Well, that's true. So here, the question is, does false imply that true implies true? Well, false implies true. This evaluates to true. So really, we have false implies true. That's what we're looking at. And if you just look at the truth table for implies, this is true. Okay, so I just picked an arbitrary combination of truth values for P, Q, and R. And maybe I just got lucky and it came out to the whole thing evaluated to true, but I didn't just get lucky. The reason it evaluated to true is that this actually is a valid rule of logical reasoning. Okay, so we expect our validity checker to return true when we ask or when we use it to check that that this proposition is valid. Okay. Now, here are some rules that involve negation. And these are some of the more complicated rules to think about. So let's look at this first one. It's called Modus Tollens. And this is, again, this comes from, you know, the Greek. What this rule says that if whenever P is true, Q is true, then if Q is not true, then P must not be true. Okay. You're saying to yourself, oh my God, this is all, you know, this symbolic weird stuff. Just take a second and just substitute P and Q for meaningful, you know, kind of like intuitively meaningful propositions. Okay. So suppose that P means it rains and Q means the streets are wet. So what this says is, if it rains, then the streets are wet. If it's true, well, here's the main implication, right? So if this, then this. If, whenever it rains, the streets are wet, then if the streets are not wet, it must not have rained. Repeat that 3 times to yourself. If it's true that whenever it rains, the streets are wet, then if the streets are not wet, then it must not have rained. Think about it. If it's true that whenever it rains, the streets get wet, and you look at the streets and they're not wet, what can you conclude? It must not have rained. Because the streets are dry, and you've assumed that if it had rained, the streets would be wet. So if the streets are dry, it must not have rained. Okay? So that's what this rule says. And that makes sense, right? I mean, intuitively, that kind of reasoning makes sense. And it's really important to see that the order of P and Q gets reversed here, right? If, whenever it rains, the streets are wet, then if the streets are not wet, then it must not have rained. Now, if you look down a little further down here, here's a rule, and I'm going to copy and paste it up under Modus Tollens. because it's so closely related. And this basically says, let's look at this rule. We don't reverse the order of the P and Q in this sentence here. So what is this saying is, so let's start by saying, we expect this to be, is valid. We expect this to be is valid. Seems like a reasonable rule. How about this one though? If whenever it rains, the streets are wet, then if it hasn't rained, the streets must not be wet. Does that sound right? If whenever it rains, you know that the streets are going to be wet, and you know it hasn't rained, then can you deduce that the streets must be dry? And the answer is what? And the answer is no, you can't. Why? Because the streets might be wet for some other reason. Okay, maybe somebody has their sprinkler running and it's spraying water in the street, or water has fallen off of the air conditioning unit of somebody's car. Or somebody has washed their car in their driveway and there's lots of water running down the street. Or maybe the fire spigot is open and there's all kinds of water rushing into the street. Okay, so this is not a valid rule of reasoning. This is what we call a logical fallacy. Okay, we expect that this is not valid. And what's really interesting is if you write the truth table here, then you'll find that you don't get true in every row. So let's actually go ahead and do that. And let's see how that works. Okay, so we have P, we have Q, we have, and let's write out, let's have a column for P implies Q. Let's have a separate column for not Q implies not P. And finally a column for the overall statement here. Okay, so good. Sometimes when you're writing truth tables, it's helpful to have some columns for the parts of the overall expression that you're trying to evaluate. So P and Q are only two variables. So we've got false, 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 false. In the next row, we've got false, false, true, true. In the next row, we've got true, true, false, false. And in the next final row, we've got true, 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 true. And those are the only four interpretations possible for these two propositional variables, these two Boolean variables, if you want to think of them like that. So what's the value of P implies Q when P is false and Q is false? Well, this is true, because P being false means that this implication is true. Same here. So we've got that P implies Q is true here because P is false. Now here we have P implies Q has got to be false because true does not imply false. True implies false is false. And finally we have true implies true, and we know that that's true. Okay, so P imply under each of these four interpretations, the antecedent here has these values: true, true, false, true. Okay. Over here, what do we have? Well, we have not Q, so we have true implies not P. True implies true. That's true. Not Q, false implies not P. True. So false implies true. That is true. Help me to make sure I don't make a mistake here. Not Q implies not P. Not Q is true, not P is false. So true implies false. Aha. So we have false here, if I'm not mistaken. And finally down here, not Q implies not P. Well, false implies false. That's got to be true, because false implies anything. Okay. Now we can fill in the last column of our truth table. P implies Q implies, oh darn, I've got not Q implies not P here. Sorry, let's fix this. I wanted to put not P implies not Q here, so we have to go back and fix. We have to go back and fix this. Sorry about that. Okay, so not P implies not Q. Not P is true, implies not Q. True implies true. That's true. Good. True implies false. Aha. that's false. That one's false. False implies true, that's true. And false implies false, that's true. Good. Okay. Finally, does this imply this? True implies true, that's true. True implies false. Aha. That one's false, right? False implies true is true. And finally down here, true implies true is true. Good. So it is not always the case that reasoning with this rule is valid. In particular, if P is false and Q is true, then this is not true. Let's think about that case. Well, translate it into English yourself, okay? We're going to run out of time here, okay? The point is that this formula is not a valid rule of reasoning because under some conditions, it fails to produce the right answer, right? It's not invariably a valid rule of reasoning, okay? So we expect that this is going to be reported as not valid. So we'll say not is valid here, like this. And instead of using an exclamation point, we might as well be like logicians and use the right symbol. Okay, so we expect that this is not going to be valid. Good. More rules involving negation. Negation elimination basically says that if not P is true, then P is true. So if it's not raining, then what? It's raining. Okay, I think we can dispense with this one pretty quickly. We expect this to be valid. What's really, really interesting, and we don't have time to get into this, is actually not a valid rule. In general, in a constructive logic like the logic of Lean, there's an easy way to make it valid by just adopting an axiom that says it is valid. But in the constructive logic of Lean, this isn't true. But in propositional logic, this is a perfectly valid rule. And we call this negation elimination because it's a rule that allows us to get rid of double negations and just, eliminate them. Okay, so if I'm not happy, then I'm happy. Okay, the English doesn't always work out quite right. If I say I'm not unhappy, that actually still has kind of a negative connotation in English, right? If somebody says, how you doing? And you say, well, I'm not unhappy. That's kind of hedging. Okay, but in logic, if you say I'm not unhappy, if I'm not happy, then that means that you are happy. Okay, so you have to be a little bit careful again, going back and forth between English and logic. Okay, the law of the excluded middle is another law that's not valid in the constructive logic of Lean, but we expect it to be valid, and it is valid in propositional and what we call classical predicate logic. It basically says that given any proposition P, it's either true or it's not true. Okay, either the proposition is true or the negation of the proposition is true. Suppose P means it's raining. Well, then is it true that it is raining or it's not raining? Yeah. If the proposition P means Kevin is from Charlottesville, is it true that Kevin is from Charlottesville or Kevin is not from Charlottesville? Classically, yeah, that's true. If P means 7 is a prime number, then is it true that 7 is a prime number or 7 is not a prime number? And of course, one of those conditions holds. We could have a long conversation about why it sometimes makes sense not to adopt this as a valid rule of reasoning, but we don't really have time in this semester to get into that. Okay, so there's another important rule for you. Okay, now here's a really interesting one. This basically says that if some proposition implies false, then that proposition must be not true. Okay, because if that proposition P were true, well then, yeah, good, right. So the way to think about this is, if I assume that P is true, and from that assumption can deduce that false is true, then something has gone wrong. And so, uh, uh, and so it must be the case that my assumption that P is true is invalid. Okay, and so it must be the case that P is false. And this is the rule that underpins a proof technique that is important, called proof by proof by proof by proof by negation. Okay, so we expect that this is valid. Okay. And finally, we're down to a couple of last rules here. I'm going to skip the last three. I don't think it's important to cover them, but let's look at these last two and let's ask ourselves if we think they're valid. If P implies Q, then Q implies P. Okay. If whenever it rains, the streets are wet, then if the streets are wet, then it must have rained. We can already, based on our previous conversation, rule this out as likely not valid. So we expect that this is not valid. Okay, see if you can come up with an example or two of your own. If whenever somebody is nice, everybody loves them, then if everybody loves somebody, that person must be nice. Well, no. If they're nice, everybody loves them, but people could love them for other reasons. Okay, so this is a rule that is not a valid rule of reasoning. This is a logical fallacy. And one of the purposes of the invention of logic was to be able to recognize when in an argument, in the forum, in Greece, or on grounds, there's some argument going on. People will sometimes try to sneak by with arguments of this kind, right? And logic helps us to catch those arguments and to rule them out as not being valid arguments. Okay. And finally, we have this rule. If P or Q is true, then if P is true, Q must be not true. Okay. So this rule basically says, well, if P or Q is true, well, that sort of maybe means that one of them is true. So if P is true, then Q must be not true. And that is not a valid form of reasoning, because of course both of them can be true. If P or Q is true, well, that could be the case because both of them are true. And so in that situation, it's not the case that P being true rules out Q being true. Both of them could actually be true. And so here's another logical fallacy, and we expect this rule of reasoning not to be is valid. Okay, and we'll just skip these. I'm just going to delete them from the file. Okay, so great. So here what you have are a couple of things. One, you have an enumeration of most of the fundamental rules of proper logical reasoning, okay, whether in propositional logic or in predicate logic. You have the foundations for an understanding of proof construction. Okay, so for example, to prove that, well, let's not go there. Let's not go there. Okay, and importantly, for our purposes here, we now have a set of test cases for what we're going to build next, which is a validity checker. Okay, and so this is actually, the rest of this is going to go by pretty quickly. I want to open up a file over here in this window that I've prepared for you, and I will show you this file. It's called px_validity_test.lean. So here we have px validity. This is the file that we just went through. Okay, and now I'd like to show you what, test cases for what we're going to build. We're going to build a function called isValid. We give it a proposition as an argument, one of these propositions that we've named over here. Okay, and so I'm going to delete these last three because I've deleted the definitions from this file on the left. Okay, And the question is, do each of these expressions evaluate to true or false? Okay, here we evaluate the application of this function that we're going to build. In other words, we're writing the test cases before we build the function. We expect this application to return true because we expect that the rule we've called and intro, which says if P is true, then if Q is true, then P and Q is true. Okay, we expect that to return true because we believe that this is actually a valid rule. On the other hand, this fallacy that we've called affirm consequence, or that the logicians have called affirm consequence, we expect that this returns false because this is actually not valid. It's not the case that if P implies Q, then Q implies P. It's not the case that if whenever it rains the streets are wet, then whenever the streets are wet, it's rained. Because the streets could be wet for other reasons, okay? Okay, so even if this is true, this need not be true. So this implication doesn't follow. Good. Okay, so you understand now what we're going to build, and now we're just going to build the rest of this. And the test question here will involve just completing parts of the implementation that we're going to produce here. Okay, so here we go, and I promise this isn't going to take too long. So now we're going to build our propositional logic validity checker. And it will work by taking a list of all interpretations, a list of interpretations containing all possible interpretations for the three variables in our expressions, right? We have V0, V1, and V2. So we're going to write how many interpretations? 8. Okay, so, and that's all the interpretations we're going to need. We're going to assemble them into a single list. Okay, and then the idea is that we will determine whether a proposition is valid by evaluating it under each of the interpretations in that list. And if we get true for all of them, just as we got trues in all of the columns for valid propositions here, we got true, 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 true. This is the result of applying our evaluation function to the formula under all possible interpretations. If we get all trues, then we report that the given proposition is valid, otherwise it's not. Okay, and so here we go. So let me repeat again. We're going to build a validity checker. It'll work by taking a list of interpretations containing all possible interpretations for the variables in our expressions. In other words, the list, the number of elements in the list is the number of rows essentially in a truth table with 3 variables, P, Q, and R. If a proposition doesn't use R, it just gets ignored. Okay. We'll then use p-eval, our evaluation function from our px file, to evaluate a given proposition under each of those interpretations. And if and only if the result is true for each possible interpretation, our function will return true, indicating that the proposition is valid. Otherwise, it will return false, indicating that it's not valid, that it's not a valid form of reasoning in general. Okay, so task number 1 is to define all possible interpretations and then to assemble them into a single list of interpretations. So we're going to make this not really very hard for you, right? So let's start off with the first 2 of 8 interpretations. Okay, we're going to call it interpretation 0. So you're going to basically implement interpretation 0 through interpretation 7. Okay. And in interpretation 0, the first variable, V0, is assigned, if you want to think of it that way, the value false. Same for the second variable, same for the third variable. And then we have a rule here to cover all of the other infinitude of variables whose values we don't really care about. We just default them all to V0. Now, if we think of false as equivalent to binary 0, then false, false, false is 0, 0, 0. In binary, that's 0, and so I use that as part of the name of this function. Okay. The second interpretation has V0 being false, V1 being false, V2 being true. If I think of that as 0, 0, 1, then we can use 1 as a part of the name of this function. Okay, so your test question here, not really very hard, is to define interp 2 through interp 7. And this is just an exercise to make sure that you know how to do this and to, cement your understanding of what it means to consider all possible interpretations, all possible semantic interpretations for a syntactic object, this proposition that lives in the world of the syntax of our language of propositional logic. Okay. Once we have all 8 of those interpretations, we're just going to assemble them into a list. And to make this easy for you, I've started this off. Okay. I'm going to define interps to be a list of objects of this type, and this is the type of our interpretations. They are functions, of course, from variables to bools. So we're going to build a list whose elements are functions, a list of functions, okay? Each function taking a variable and returning a Boolean value. And that's exactly what these interpretation functions here do. Okay, so you remember that the constructor, there are 2 constructors for lists, nil and cons. So a list is either empty, nil, or it's cons, head, tail, where head is the first element in the list and tail is the rest. You've spent a lot of time on this, so I'm not going to review that in any detail. If you don't remember, go back and look at all of the material we covered on lists. So here's my list with only the first 2 interpretations in the list. And your job is to make sure that this is a list of 8 interpretations, okay, when you're done. So we have here, it's cons. Here's the head of the list. It's this very first interpretation, followed by a smaller list that starts with this second interpretation. And at the moment, those are the only ones that we have. So the rest of the list is nil. And in order to finish this list, you need to replace this with list.cons. The next element in the list, we'll call that the head, the remaining element in the list, the tail, and go on from there. But for now, this is just list.nil. Okay, so this will re-exercise your understanding and ability to write lists in Lean. Now, I should tell you that Lean does have a nice notation. It has a concrete syntax for representing lists, and it uses just square brackets and comma separated values. But I don't teach you that because in order to write functions that process lists recursively, this is the structure that you really need to understand. Once you fully understood this structure and how to write algorithms that exploit this, this recursive structure of lists, then you can start to use the nice notation, okay? And so here's the rest, okay? So let me jump down to this function here. Here's the function that's going to determine if an expression is valid. So that's the function that we're testing over here, okay, applying to each of our propositions. It takes a proposition and returns a bool, true if the proposition is valid, which is to say true if the proposition is true under each of its possible interpretations, okay, and that returns a bool, true if the expression is valid and false otherwise, okay? And the way that this function works is it takes an expression, here we call it E, and it simply calls this helper function here, okay, passing it the expression E, that's this, and this list of all possible interpretations for 3 variables, okay? Okay, so think about that. We call this helper function, passing it the expression, and the list of interpretations under which we want to evaluate this expression E. In fact, maybe I'll call this EXP, just so that it's clear that that's an expression, okay? So given an expression, we call the helper function, pass it the expression, and pass it the list of interpretations under which we want to evaluate that expression. And we want this function then, the helper function, here it is, takes an expression and a list of interpretations and returns a bool, okay? And your test is simply to complete the definition of this function. Okay, so let's look at the definition of this function. We want it to return true if evaluating this expression under each of the interpretations in this list returns true. And so we're going to use B and to combine the Boolean values that we get when we evaluate this expression under each of the possible interpretations. Okay, so we're going to have two rules here. If we evaluate an expression under an empty list of interpretations, we need to return a Boolean value, and that's what I've left as a blank here. Okay? And you need to come up with essentially the right Boolean value to return when the list is empty. And you already know how to do this. We've already done this actually. Okay? You need to return essentially the identity element for the function being used to combine the elements in the list. So we're using B and here. So really you want the identity element for Boolean and as an answer here. Okay? If you are asked to, and here I'll use exp again since I used that below. If you're given an expression, exp, and a non-empty list of interpretations with an interpretation h at the head, h being of what type? H is an interpretation. So h is a function that takes a variable and returns a bool. Okay? And then t is the rest of the list of interpretations. In other words, if you apply this function, isValidHelper, to an expression and a non-empty list of interpretations with h as the first interpretation and t as the rest of the interpretations, then what you want to return is the conjunction, the application of B and, to two values. Here is a value that is the Boolean value that you get. Listen carefully here, and then you'll know how to write this. You need to fill this slot in with an expression that returns the result of evaluating this expression under this interpretation. So what do you write here to evaluate given expression x under the interpretation h? Okay, so this, in other words, returns the Boolean value. It returns the Boolean value that you get when you evaluate this expression using the first interpretation in this list. Okay, so suppose that's a true. Suppose that this expression is true under the first interpretation in this list. Well, you want to compute the and of that true with the result that you get by continuing the process for the rest of the list of interpretations. Okay, so in essence, this is going to be one of these reduction functions, a reduce function. That's what this is. It's going to reduce a list of interpretations essentially to a list of Boolean values that you and together in order to determine whether or not this expression evaluates to true under every interpretation in this list. Okay, so that's basically it. Now, almost done, but I want to repeat it one more time. This expression, this whole, needs to return a bool. You have some functions you can use here. H is an interpretation of type var b to bool. Okay, that's your first interpretation. X is an expression. So you need to evaluate that expression under that interpretation here to get a bool. Okay, and then do something here that takes care of the rest of the list. Eventually, you end up with an empty list, and you need to return the right Boolean value here so that the answer that you obtained from all of the preceding parts of the list is not changed when you and it with that final Boolean value returned for the empty list. Okay, And again, this is stuff that you should understand. We've done this. We've covered this material. There's not a lot of work for you to do to answer this question, but this is the final test question for you. Okay? And if you don't remember how to do it, go back and look at, what we covered when we covered this material earlier in the semester. Okay, everybody? Good. Details to appear on Colab, okay, for submitting all of this work. Okay, thank you very much. Talk to you soon.